Hi, welcome everyone. This is now our second online edition of the Kitchener-Waterloo Video Tech Meetup. I'd like to welcome all the guests locally from the Kitchener-Waterloo area that are attending remotely, I guess, as well as those, I think there are a few from Toronto, and there may be some, Ali, I believe one of our speakers is all the way talking from Turkey, and we may have some people from the West Coast. So for those unaware, the Kitchener-Waterloo region is an hour drive from Toronto. Last year, I attended a video conference some people have heard of called Demuxed, and saw that there weren't any video meetups in Canada, and so I decided to change that and start this one. Since KW is, the tech capital of Canada, and SimWave is in KW, I thought it would be a great fit. Like I said, this is our second edition and our fifth meeting overall. So just want to preface, if you want to see any topics discussed or want to share something that you're working on, let me know and we can work together to set something up. So with no further ado, I'd like to first introduce our first speaker. Dr. Ali Begen is a technical multimedia consultant who has over 20 years of video experience. He's a senior member of both the IEEE and is part of the Dash Industry Forum. He joins us today to talk about bandwidth prediction and chunked low latency streaming. So welcome, Ali, take it away.
All right. I suppose you can see my slides?
Yep.
All right, perfect. Good morning, good afternoon, everybody. I will be talking about bandwidth prediction for adaptive streaming, especially for low latency applications. In non-low latency applications, we know how to do it pretty well, but it is a bit a challenging topic to do it at low latency because the data transfer is not really working the way it works for the regular non-low latency applications. So this is a project we started a few years ago. We had our first paper published last year in one of ACM's workshops, ACM Nostrum 2019. And actually that paper got one of the Dash IF Excellence in Dash Awards last year. And later on, we kept working on it. And just 2 weeks ago, there was ACM Multimedia Systems conference. It was supposed to be in Istanbul. I was the general co-chair, but due to the COVID-19, we had to have it virtually online. And there was a grand challenge sponsored and organized by Twitch on this very specific topic. And we also participated in that challenge. And we didn't win it, but we were the runner-up. And I will give some details about what we did, what we found out, and some typical results from our current code. Everything is accessible from the papers, and the code is already on GitHub. And I will share the links at the end of the presentation. Okay, so bandwidth measurement is a tricky topic, as I mentioned, especially in low latency applications. It's you need to do a good job, otherwise, the way you react to bandwidth changes might create problems for you. For example, if you don't have sufficient bandwidth, but if you still insist getting a high quality video, you might end up emptying your playback buffer and then you will get a stall, right? That's not really what we'd like to have. So Twitch, as you know, is a very popular video service, especially for online gaming. And there's tons of data, and most streams are running at low latency. When we say low latency, we are talking about latencies about 2 to 5 seconds. I mean, mostly less than 10 seconds. And latency means any the delay, the entire delay between the capture all the way to the playback. So anything in between contributes to the latency. So we started doing some testing with the Twitch data. Here I am showing a bandwidth regime that we applied to this Twitch stream, and the way the Twitch stream was reacting was as follows. So the client was measuring more or less the bandwidth shown in the yellow crosses, and then the client, based on that, was picking a bitrate close to 2 megabit per second. So this was happening also when the bandwidth was about 5 megabit per second, when this was also happening around 1 megabit per second available bandwidth. So this was really a good job. And this avoids clients to upshift when there is excessive bandwidth available in the network. And then if you don't do a good job, you won't downshift, and then you will get a stall because your playback buffer is pretty short in low latency. And because of these challenges, what happens is most initial low latency deployments have seen a single bitrate video. So not really multi-bitrate, but single bitrate video. So not really adaptation existed in those applications. So in our Nostrum paper, we tried to explain this by this visual diagram. So I have a football game on the top. The time runs from right to left, and then what I'm doing on the server and origin side is the encoder and the origin side is I am capturing the frames and then encoding them and then packaging them at every D duration, let's say 2 seconds, 6 seconds, whatever your segment duration is, and then different colors are representing different segments. If we are doing non-low latency streaming, what happens is that the client, joins the live session, fetches the manifest. It could be the HMPD or HLS playlist. You make a request to one of the latest available segments, and in this case, you will be asking for the green one because the orange one is still being generated, so it's not available to the client. So if you ask an earlier segment, you will also get it, but your latency will be higher. So in this case, we ask for segment number 1, and then we get it. All these individual frames, chunks, whatever you want to call it, we will define them later. You will get in a single HTTP response. And the time between the request and the end of the download time is your segment download time. And what almost all clients implement today is they divide the segment size by the segment download time to get a sense of the available bandwidth. And then after a while, once the segment 2 is available, you ask for segment 2 and then get it, and then you do the same calculation again. And then over time, you get a time series of bandwidth samples, and then you do smoothing, you do exponential weighted averaging. You can do whatever you want, but eventually you will get a sense of what's happening in the network. In the low latency case, as you know, we are doing chunked transfer encoding for dash low latency and DVB dash low latency. So the way it works is, just the HTTP 1.1's feature, we make a request, and here we are not making a request to the green one, but we are making a request to the orange one because that's even lower latency, right? We make a request, the data is not fully available. Whatever is available, I will get in a burst, and then the remaining data will come in pieces, right? And then later on, I will make the request for the segment number 3, and then I will get what's available on the server, and then again, remaining chunks piece by piece. And usually what happens here is that your segment download time, due to these idle times between the chunks, is going to be pretty close to the entire segment duration. It doesn't really matter whether you have like 10 times more bandwidth than this encoding bitrate. You will still get it around this duration of D because the data is being generated at that rate. So in this case, we are not really network limited in terms of your throughput, but we are source limited. So when you are source limited, doesn't really matter if you have a fast fiber or like a ultra high-speed LTE connection. You will still be stuck at that low speed. And that's the reason why Twitch and other earlier applications that deployed low latency they weren't able to upshift to higher quality video, even they had higher bandwidth available in the network, because the client never actually understood or observed that there was such bandwidth available. So we have to deal with this problem on the client side and come up with an algorithm. So the paper I am referring to is ACM Nostrum, which is cited here. And then there was an extension to that, which was just published earlier this month in the ACM Tom journal. So our method is called ACTE, ABR for chunk transfer encoding. So the way it works is, first of all, we try to make a good bandwidth measurement. If your measurements are not good, then you will not do a good prediction. We use also a sliding window. Usually our window size is 3, and we do a moving average. But the way we collect the bandwidth measurements, it's the critical part, which I will show next. And then we just don't stop there. We also predict the bandwidth into the future. And for that, we have developed an adaptive filter mechanism based on the RLS algorithm. And then based on that, once you know what the bandwidth is going to look like in the future with a certain probability, you can do a proper rate adaptation. And if you do good measurements, if you do a good prediction, well, most likely your rate adaptation will be pretty good as well. That means you will be able to upshift and downshift over time based on the bandwidth changes in the network. So this is just an example over here. When I ask for a segment, I will be getting not the entire segment, but I will be getting these individual chunks. And I don't want to get into that because of the limited time, but these are CMAF chunks, and they are mapped to HTTP chunks for HTTP 1.1 transport. So this is just an example. This is one particular segment, and let's say I have chunk 4 here, chunk 5, chunk 6, and chunk 7, and they have their own individual sizes. They don't need to be equal in terms of sizes. So each chunk has a beginning time denoted by B, and then end time denoted by E. And I know when the chunk is downloaded in my HTTP JavaScript client because of the HTTP fetch API, and I can also determine the size of the chunk because of the data I received. But the problem is I don't have access to the information that gives me an idea about B, the beginning time. If I also know B exactly, what I can do is, the bandwidth, the download throughput is size, which is known, divided by E minus B, right? End time minus B. Since I don't know B, I need to find a way to approximate it. That's the tricky part that we are solving in this problem. The question here is, when the chunks are transmitted back to back, like the chunk 4 and chunk 5 over here, that means the data is just coming to you at the network speed. But once the chunks are separated from each other, that means they are source limited, and that's not really the bandwidth we would like to measure, because source limited rate is not really interesting to me. That's more or less the video encoding bit rate given in the manifest already. So there's really not much information in there. So what I need to do is, I need to identify which chunks are good for bandwidth measurements and which chunks are not good for bandwidth measurements, so that I can discard them. There's a nice algorithm in the paper for this, but the way we approximate is, for each chunk we try to compute its download rate, but then obviously we don't have its beginning time. What we do is we take the previous chunk's end time. If you see over here, instead of P5, we take E4, for example, right? So that's just an approximation. And then if this download rate is close to the average segment download rate, which is my encoding bit rate, plus minus 20%, well, I say that there's a significant idle time between these two chunks, and this is not a good chunk. I just discard that from the bandwidth measurement. Otherwise, the idle time is negligible. That's a good chunk. I should be actually using that for bandwidth measurements. If I do this, I can use the last 3 measurements, good measurements in my sliding window to come up with a better idea of what's happening in terms of bandwidth. And based on this, I run my RLS algorithm, and then I predict the bandwidth into the future, right? So the last 3 measurements have been these values. What is the expected value for the bandwidth into the next segment time, so that I can make a better rate adaptation. So the algorithm was implemented in Dash.js, and we compared it with a bunch of other algorithms existed at that time. And some of these were not really tailored for low latency, but still people use them for this purpose too. So segment-based last bandwidth, chunk-based exponential weighted moving average, chunk-based sliding window moving average. And then if you know Will Law from Akamai, his proposal was, I can always ask as a side download the last, not the last segment, but the earlier segment from the CDN. And since it's already cached fully at the edge of the network, I can just download it to predict my bandwidth. Well, that was a very simple approach, but it has a certain overhead because of the active probing. There are a bunch of results over here. I'm not going to get into details. I'll just give a couple of enhancements that we did in the last few months. So the idea here is just to, comparing in terms of what bit rates they were able to stream at, these different algorithms, their prediction accuracies, and then, what latencies they were able to achieve. For example, ours was able to achieve a latency about 2.5 seconds, whereas the others were more than 3 seconds. And I mean, this last segment download was over 5-second latency. And the QoE, there's a certain formula that we use in the paper, in model. And the QoE obviously is what matters for the end user. And we tried to be the best in terms of the QoE, and we were able to, because we were able to track the bandwidth more accurately. Now, coming back to the extension of this work, as I said 2 weeks ago, there was this MMSys conference. It's the ACM Small Media Systems Conference. And Dash and the streaming type of video topics are one of the hot topics in this conference. And Twitch started this grand challenge earlier this year. And then all the details, testbed, the code, everything is available on this link. And since the conference is now over, all the presentations are also available on YouTube if you want to have a look at it. So we participated in this challenge. I had one of my students, and then I collaborated with my dear friend Roger Zimmerman, who is a computer science professor at the National University of Singapore, and then also 2 students of his, Abdulhaq Mentaleb and May Lim. Abdulhaq just finished his PhD, and May is she's working towards her PhD degree. So we were a team of 5, and we tried to win this challenge, obviously. So the way the problem was formulated was more or less the same thing. The Twitch environment, we have a certain source, we have different network parameters, and the guy, the solution that predicts the bandwidth the most accurately and gets the best quality at the end of the day wins the challenge, right? They did their own evaluation. But for our per paper and for our own internal comparison, this is the QoE model that we adopted. This is not really our QoE model, but this is a combination of different QoE models from the literature. So there are things like the bitrate you pick, the latency, rebuffering time, your playback speed, whether you slow down or you accelerate, and so on. And what happens if you have a stall, and those kinds of things. We proposed 2 modes, heuristic-based and learning-based. Heuristic-based was more or less based on the fast MPC algorithm, which was suggested in the literature earlier. And it's trying to, based on the QoE model, is trying to come up with the best decision for the ABR, right? Should I switch to another bitrate? Should I stick with the current bitrate, and so on? And while obviously you need to satisfy the latency requirements. And what happens is you, at the end of the day, you permute all the options, and then you try to calculate the expected outcomes, and whatever gives you the best outcome, you pick that one, and then you move on to the next state. The Learning-based one was based on self-organizing maps, so that's more like a machine learning type of algorithm. So we implemented this for our problem, and we wanted to see how well it will perform against the heuristic-based one. Obviously, training is important here, and your model is only as good as the training data. So, but I mean, we survived with the data we had from our own connection, and as well as from Twitch. So the ABR selection criteria, again, it's it's one of the important topics. If you don't know what's going to happen in a network, if it is not really stable like a cable network, maybe it is more like a wireless type of network, well, maybe adjusting to certain conditions might be done better if you use learning-based algorithm. Also, if your QoE model is a bit obscure, like you don't know what is going to impact the QoE at the end of the day, well, learning-based model still works better. Otherwise, you can compare both rules, like learning-based as well as heuristics-based, and then see which one works better under the given conditions. But that's obviously a brute force approach. And then eventually, our next target is, can we actually identify the scenarios where one will outperform the other, and with a certain probability, so that we can just decide very quickly. So the way we made this work was, we changed the playback control module in Dash.js client, and that was the client we were asked to work with. And we implemented all the things that we put in the paper, and then we tried to, for example, implement this variable playback speed, so that in case you are too close to the latency target, you can slow down a bit just to grow your buffer a bit, so that you can make better decisions. Or if you are too far from your latency target, what you need to do is, you need to, maybe accelerate the playback so that you catch up with the live broadcast, so the latency drops. But then you need to avoid the installs during that time. So, there was a certain algorithm over there. This is just showing an example. If your latency is low enough, you can slow down. If it is high, then you need to speed up. But depending on the amount of buffer, data in the buffer, you speed up at different bit playback rates. So, we hit this algorithm from Octave, but there were a lot of corner cases where it wasn't really working very well. So we had to work on that and improved it a bit. So the same problem again, we have different chunks for the same segment, and chunk download beginning time, and then end time, and the chunk size. E minus B indicates your download time, and unless you know exactly what E and B are, you won't be able to compute the download time, right? So in this case, what we did was, okay, well, maybe we can do something smarter. What we end up doing was, as the chunk data was coming in, we were parsing the data in real time, and we were looking for a move box. If you know what CMAF is, move and end dot, that's a chunk for you. So as soon as you see a move, you say that, okay, that's the beginning of the chunk. And then since I know the end of the chunk and I know the size of the chunk, I can do a better estimate or measurement of the bandwidth. And I, again, get rid of the bad chunks. I keep the good ones, and then I try to get a better and more accurate bandwidth measurement. So the code is over here. We have a couple new modules for the Dash.js, so you just need to incorporate them in your code. But we made some changes in the playback controller, so that's what you need to get from our website as well. We are continuously making some improvements over here, and obviously we will keep working on it. So just to give you some results, in terms of learning versus heuristic, well, we were, optimistic that learning will be better, and since it adjusts based on the needs and as well as based on the dynamic behavior happening inside the network, we realized that learning was quite good in terms of achieving a decent quality. You don't need to pay attention to the absolute values of these, but relative values of these QoE metrics. And then there was still obviously some rebuffering because the latency requirement was around 1 second. So it was extremely low latency. That was really pushing the limit. So what we saw from the results is that learning-based algorithm provides a pretty good stability in terms of quality and the bitrate adaptation, and it's comparable to heuristic-based. Although there are some cases where one can still outperform the other. So that's one of the things that we are looking into now. And just to give you an idea about how accurate our bandwidth prediction was, these are the network traces given by Twitch for the Grand Challenge. And here we are comparing 3 algorithms. So actually not 3 algorithms, but 2. So the blue one, if you can see the lines, and you can check them from the paper, that's the actual throughput, and the green one is ours, our method, and then the red one is the default dash.js client at the moment. Obviously, dash.js is also an active project. They are actively working on to make this bandwidth prediction better and more accurate. So these things will hopefully change in a short amount of time, but still the accuracy of our method was pretty good. We had some certain problems with our playback module in terms of adjusting the playback speed. So I guess that's one of the reasons why we lost the Grand Challenge, but still in terms of bandwidth tracking, we did a pretty decent job. So that's the end of my talk. This is a fairly interesting and detailed topic, but I recommend you to look at the papers, and you can always send an email to one of us or all of us. My colleagues and are all listed here, and this is the GitHub page where we keep our code. That's the end of my presentation. Thank you.
All right. Thanks, Ali. So yeah, if anyone has any questions for Ali, you can ask them in the chat. I just posted something in the chat, or you can just unmute your mic. I thought that was kind of interesting. I have a few questions myself, if anyone doesn't have any.
Yeah, I have a few questions too, but I just wanted to bring up only 2 questions. The one thing is that in your experiments, how do you typically measure latency?
So the latency is, again, the definition is the difference between the playback and the capture time, right? So the easiest way is obviously to use a time-coded video source. So let's say you are capturing a video of a clock or like a digital timer, right? Mm-hmm. And once you play it, you can always look at the difference between two time instances, and that gives you the latency. And in practice, obviously, not everything will include a timer, and the way we deal with it is that there's a box MP4 box, atom box, yep. PRT, producer reference time, and that's where the capture time or encoding time or packaging time. I mean, there are different options where you can put a certain timestamp into that box. And on the playback side, once you look at that, you will realize how long your latency is. Obviously, this requires all those entities to be UTC synchronized, but that's more or less required anyway for other purposes in live latency, low latency streaming anyway. When you are asking, when you are trying to determine which segment is the latest and so on. So if the UTC clock synchronization is available, what we put in the metadata in the source video it will help the client understand what the latency is.
Okay. And can you explain more about one of the slides you mentioned about the learning approach and heuristic approach? And then you mentioned if you don't rely on your QE, then you can take a learning-based approach, if I'm not wrong. I'm not sure whether if you can go back to that slide.
Yeah, sure.
Yeah, this is the part that I don't understand. Why when you don't trust any QE, I think it's slide number 18.
This one?
Yes, yeah. You mentioned that if you have obscure QE model, then you can use learning based.
Yeah. So this is an interesting question, and you know, I don't think I have the perfect answer for it. But what can I say is that the QE model, for example, we adopted in this paper and in our own submission was this one, right? You know, as you can see, there are a bunch of parameters over there, and then a bunch of things that you measure, and then you just put it there. You try to calculate a QE value. And this is by no means you know, valid for everyone or for every scenario, every type of content. You know, it's not like a universal QE model, right? That's what I'm trying to say. So for certain types of content, you know, latency might have a much higher factor or weight, right? And you know, maybe the bitrate you know, changes, upshifts, downshifts will have less impact on the QE, or vice versa. Sometimes stalls are very important, but sometimes stalls are not that important, or startup delay is important, or maybe startup delay is not that important. So the QE model, if you don't know what you are working towards in terms of, you don't have an objective function to optimize against, then, you know, sticking with the learning-based makes more sense, because, you know, the heuristics we develop will actually be using this QE model, and if it is not really valid for you for your application anymore, that's not going to really help you much.
Okay.
Make sense?
Yeah. Yes.
Ali, I had a question about the playback speed. So I'm not too familiar with how sort of JavaScript players work, but are they to sort of maintain consistent QE? Is it actually playing the video at those speeds, and it just
Yeah, so
okay,
you slow down the video or you accelerate the video, and you need to do the same thing for audio as well. So it's essentially media playback. Now, 1.1, I mean, the middle one, 1.4 over here is, for example, it's a bit maybe overstretching. And if you have seen YouTube, you know, they started implementing this, Netflix does it too. You know, you can go up to higher speeds, but then you need to start processing the audio as well. Otherwise, if you don't preserve the pitch, you know, people or, you know, other sounds are gonna sound very funny. So if it is not really like, you know, two people talking to each other, if it is not really speech or just natural sounds or some music, you know, acceleration will work just fine. You just play with the decoder clock, and you simply accelerate or deaccelerate the playback. It is very easy to do it on the JavaScript level.
and that's most JavaScript players do that in terms to even when
No,
your
I
playback
mean,
speed is targeted at like real time, one times.
Yeah, you know, I mean, this has become a bit more important, or maybe attractive once we started doing low latency, right? Like if we are doing you know, regular streaming, not really low latency, then you almost never need to play at different rates. Like you don't need to change the playback speed. But at the low latency, you know, we need this because remember, if you are running out of data in your buffer and your buffer is extremely short, right? If you are asking for a 1 second latency, your buffer is going to be like less than half a second. So if the data doesn't arrive, you will stall right away. So if there is such a risk, you start reducing the playback rate just to make up some more time, and then hoping that the next chunk or the next frame, whatever, will arrive by the time you need them, right? So, even these subtle playback rate changes, maybe they won't be noticeable to the user. Well, hopefully they won't be noticeable to the user, but you will get away and you will avoid a stall. That's why they became more important nowadays. Otherwise, for normal players, they're not going to be used that much.
Okay, great, thank you. I guess one other question I had was about the network profiles. Do you know like what those typically map to? Like, is it a cellular or 5G or
No, these were
local
just
or...
random made-up network traces by Twitch, just to, they wanted to give us a certain, input so that everybody could actually try to test their algorithms in advance and see whether there was any problem. For example, cascade, right? The bandwidth drops first and then it increases again. I mean, it's just, are you able to really track this bandwidth decrease and then increase again and so on? Or like, what if there's a bandwidth spike, for example, like suddenly you make a spike and so on. So it's jitters, up and down, up and down. So it's, I mean, they were longer than this. This is just showing a small portion, but these were probably just some made up traces by Twitch.
Great, thanks. Any other questions from the group? Okay, well, thank you, Ali.
Sure.
That was a great talk. Yeah, so we'll go on to our next speaker.
Well, for anybody interested,
I'll
I can post my slides on the video dev Slack channel. So.
Right. Thank you, Ali, for reminding me about that. So yeah, so there is a video dev Slack channel. I've posted it previously, I think, on the Meetup group, but yeah, so you can join that. Ali's on it, I'm on it, a bunch of people who are sort of enthusiastic about video development, they're on it. So yeah, feel free to join. All right, thanks, Ali.